I have the pleasure to introduce the last speaker of tonight. It will be about continuing on this direction of LLMs and a perfect build-up after this first talk, because it's about how can we evaluate LLM agents for causal data science. And the last speaker is Trujillo, from who is a marketing scientist basically at Wise and also a contributor to the PyMC marketing packages and open source analytics library.
As Quentin mentioned, I want to talk about a very recent work that we have been doing at PyMC. And the main idea is start to understand what LLMs can and cannot do. So the agenda for today will be explain you a bit of how do we think that what do we think that means agentic data science? What are agentic data science workflows? What are the different players in these workflows? What are the basically gaps that we find out in the current benchmarks? How we address those gaps, and based on that, what do we find possible today? And if we have time, then maybe we can have some Q&A. So agentic data science, I want to quote directly because I really like this definition, but basically is the goal-directed, adaptive, and tool-mediated execution of data science workflows by AI systems that iteratively plan, act, evaluate evidence, and revise their approach under bounded human supervision. I really like this, not because I think that englobates a lot of the definition that we share at PyMC, but I also like it because it was made by ChatGPT. So that's a really nice thing that they can redact so precise, definitions. And one of the things that why we're talking this from a Bayesian perspective is specifically because, as it said here, the agents adapt their decision making as new evidence appear. And as you can imagine, the update of belief when new evidence arrive, it's something very Bayesian. And we were thinking, well, if they act in a Bayesian way, then we could use Bayesian tools to actually understand better what are the different decisions that they will be taking. Now, the players in these agentic data science workflows are, from one side, agents or LLMs, all the ones that we have out there. We also think that skills or the external knowledge that we provide to those LLMs, it's a player there. And then finally, we have the engine or the harness, Cloud Code, Open Code, all the tools where they are living and then the agents are using to communicate with our computers. And based on this, we start to see that every day we get like new benchmarks. LLMs are getting better and better. If you, for example, put the task from SWE to me, I probably will not score 88% like Opus 4.8. So they are definitely developing more and more capabilities. And of course, as we were talking here, we wonder, okay, then LLMs can do our job. Like, could they make causal models? And in order to do that, and I'm very happy that many of you guys already speak about marketing, we have started to make LLMs marketing questions, because marketing questions, as I said, as basically everyone here said already, are very causal. We are really interested in have causal estimates in marketing. So for that, we make a set of questions that were iteratively increasing in difficulty. And we asked an LLM to go through this workflow end to end, from just build a simple model to question the model, get estimates, refutate, and then finally make a decision from it, like a decision that could came from an optimization problem. And we basically saw what happened. And what happened is that in the initial questions, this is with Opus 4.7, the LLM scores really well. Like we did 15 trials and 14 times they were able to compile code that works. And as you can see, by the end, in the last set of questions, let's say from 4 onwards, they start to fail massively. Like the success rate went go immensely down. Of course, let me go back for a second. If you observe what's the difference between the first questions and the different question is what you guys were talking all the way. From one side, in the basic ones, is just make a model and get an estimate, and that's it. From the B side, we say like, okay, now that you have the estimate, try to refutate it. Compare, like design a quasi experiment by yourself, get experimental data from outside of the model, bring that experiments to the model, try to compare how different are the estimates that you see in the real world against the estimates that your model give to you, make sensitivity analysis or mere refutation test, like all the steps that we as scientists we will be making in order to trust this. And again, in all the second part, they rapidly fail. Nonetheless, we were wondering, okay, if they are so bad, if like just one time of 15, they are able to go through all this process, why the benchmarks are saying that they are so great? Why every benchmark says like they are better and better, you see that they are increasing. And we basically found out three main differences for that. One of, or the more important is that the benchmark are only measuring the LLM knowledge, right? And the LLM knowledge only. The agentic data process, or if you want to have an agentic data science workflow, you also need to measure the engine and the knowledge that it's being provided to the agent. So the agent itself, it's nice that he's getting intelligent. That's great. But the other two pieces are also complementary, and you will see why in a second. At the same time, these problems are very unbound. And the thing is, there is not such thing as make data science. We all have expectations and basically bounds of how to operate. Like if you're in your company, there are certain tools that you can use. There are certain environments that you will need to use. And like these benchmarks are just saying like, well, solve this problem. Doesn't matter the form, but the form matters in real life. It's not just do data science. It's do data science with the set of tools that you have available as a researcher. It's like I don't want just Bayesian models. I want Bayesian models in PyMC. I want to solve the problem with do Y, or I want to solve the problem with, I don't know, any other package. And the thing here is like they are not measuring that. And finally, a lot of the metrics are very empirical. They are just empirical rates, 15 trials, you do one for the number of success, and then that's your success rate. Or they are just measuring compilation. And that it's very falsifiable. So I want to show you with a small story that we had, and with that also touch another of the topics from the agentic workflow, and is skills. So as many as you know, we have this format of taking knowledge, compress that knowledge, and without retraining, we can impute it into the MMM. And all of a sudden, as we observe, and probably many of you observe, once you pack that knowledge, the LLMs become way better. So here is the same graph. You can see that in the first three tasks, they score almost the same. But now with the knowledge in the last task, everything goes way better. Like the LLM increase their routine, how he could do causal analysis, like I will say like a 30x than what's before. Nonetheless, still the last task, which needs to go from Q1 to Q7, question 1 to question 7, like success rate, still looks really, really low. Now, again, because this was again, we start to do a lot of more skills, and now we're all of a sudden the PRs start to look like, oh, let's just put choose the likelihood and justify it, or why we don't just add two more words and say like, oh, let's check these specific metrics and so on. Or sometimes we were just, having a set of different skills all over the place. Let's say you have the causal skill for A, for B, for C, and some other person was saying like, why we don't just have a big causal skill that is more compressed and have under the same big skill, we have all the routines that we want to follow up. And sadly, like these differences, these new strings or these new ways of structure the knowledge, were very difficult to measure. We were like, well, I think like this way works better. And then another friend or another person in the PyMC labs was saying like, oh, I think that this works better. And each of us did the test with, I don't know, 10 or 15 trials. And we were with that information, like comparing against ourselves. But the truth is that, again, once they were sharing with us, or I was sharing with them how we did it, neither of us were able to replicate the results of the other. So we were like, okay, what's happening here? And that basically boils down because we build causal models for a living, as many of you in this conference, but we were not able to measure the LLMs doing our job, and like at least not measure in a reliable way. So that's what we said, okay, let's flip the script and generate a system that is more based on how we want to measure effects. In this case, we just base it in a randomized sequential rate dynamics. So let's start to make this a more A/B test design type of approach. Let's go out from the regular empirical metrics and let's treat this with probabilities, because we trust that if we inform probabilities and how much uncertainty do we have around the measurements, we probably will have a better angle. And at the same time, let's start to not only measure the LLM, but the process as a whole. What happened if I change the LLM? What happened if I change the skills? What happened if I change the hardness? If I move any of those three pieces, something will happen. And with this type of design, I could make it. How do we get there? As I mentioned, was being a start to be more honest with our decision making. So instead of, again, have a random empirical rate, one thing over the other, we said, let's start to measure, let's say, compilation rate or probability of compilation as conjugate models. We want something that is cheaper. We don't want to do MCNC across different trials. That's very expensive, but we can have a closed form of how do we think that a metric works, and we can create a conjugate model that can give us a analytical posterior around it. So if we need to measure this probability rate between 0 to 100, we can have this beta binomial model. And what we just find out just doing this is that, well, over the same 15 trials where 14 worked and one doesn't, we usually will report like 93% of success rate. Like that's probably what will appear in SLWE. But the actual probability of that success rate being over 90% was just like 48%. So that already start to reply like, oh, this is why when I share my stuff, given this small sample size, others are not able to replicate it. I'm like overestimating in a way the actual probability, my success probability. Another thing that we needed to add to this, because this only talks about compilation, and again, compilation is very falsifiable. I will explain why in a second, but you can imagine that LLMs can just do a function and put pass, and that will make everything work. So compilation is good, code is bullshit. And for that reason, we said, well, a very Bayesian thing, it's set priors or expectations. We need to make our expectation transparent. So we designed over this process a way where you can create a reference answer. So let's say that, again, doesn't exist the agnostic way of doing something. Like every one of us has an expectation about everything, basically. And if you want to do a causal process for a specific organization, they will need to use your SLM, your libraries, the things that works for you, and do you want them to follow a specific routine so you can trust in the output. So if you're able to put all of that in a piece of code or in a piece of everything that certainly needs to be code, then you can measure how similar are the answers of the LLM through the agentic process to this new value. And this similarity is not only like semantic similarity, actually talks about the semantic, of course, but the structural weight of the code and the embedding part of the tokens. So you're measuring the similarity of to the expert answer in a more deeper level. And doing so, if you have then posterior probabilities about these similarities between the answers of the LLM and as well of the compilations, what you start to see is that as the LLM through the workflow generates code that is more similar to the expert answer, it also tends to succeed way more. So we start to see this relationship, and again, for us was a bit of evident. If you make code that looks like our code, then it's very probable that will be correct, at least in this specific field where we are experts. These also have their cavities. I will mention a few in a second, but in general, that information prove that we could teach the model, and the things that we are teaching are improving his routine to make different things or take different steps. Now, that's at the same time information itself, because now you can have clusters in all over this space, and each of these clusters will inform you different things. So let's say that, again, you are in the yellow part, which is in the high similarity, high similarity but high compilation, low similarity. That means that probably the code is compiling because it's just doing a lot of functions that can pass, but none of them are reliable. So you can use where the other trials lands to find those out. And also to wrap up, how do we get there? Like, why do we get this spreadness across this space? And that's because the models, as we were saying, need to take different decisions. And one of those decisions, for example, is how to use certain tools, how to load specific skills, what are those routines? And those depend mostly on the harness. So the harness needs to be instructive enough to expose to the LLM, okay, I need to use, I don't know, a search. I need to use this specific causal skill and so on. How can we measure that? And again, a Bayesian framework, in this case, is in the form of a direct posterior, could allow us to measure the probability of this vector of options and then understand the entropy of the model. And when I talk about the entropy, I'm talking about how decisive is the model at the time to take an action. So we want to measure, again, if he's more decisive, he's more certain about what he's doing, and then less noise is coming into the model, and it's less likely that he will end up taking a wrong decision. Doing all of that, we needed to then solve the question, can LLMs be used for causal problems? And to be honest, and now I'm showing more like posterior probabilities of success, we see that they can help a lot in initial questions, simple questions where your model is just constrained to make a model and make an analysis and get something back. Of course, as soon as you ask them the deeper question, like how can we trust in this output? How can we falsify it? What we see is that it's barely they succeed to the final one. They just arrive to 6% sometimes. Now, this is in a media mix problem. If we talk more like causal inference, can then run a quasi-experiment outside of the world and see results? Again, same causal problem, different angle. And they can run the API and have a quasi-experiment. Yes, they can do it. Once they get the estimate, they can justify it, falsify it, validate it, find another angles to say that this is not true. Barely like 10 or 20% of the times in our, again, experiments, in our setups. And one thing that we note here, by the way, and this is the most important, why we think that agentic process as a whole, it's way more relevant than benchmarks, is because here you have Claude Opus 4.6 and Mimo 2.5. Mimo is from China, is from Xiaomi. And the thing is, you can see that they basically have no difference to go to this flow. They score the same across all of these questions. And this is a pattern that repeats. And the reason is because either the skills could be, even if Opus have a better amount of intelligence, the other two parts play a huge role. And if the harness or the skills are not as good as the initial model, they could end up like neutralizing in a way. So it's like, you can think about it as if you have someone that is mediocre but has all the opportunities, could score good, and the opposite same, like someone that is good but have no skills or tools, then probably he will score bad. So the whole process matters, and what we see is that there is no difference between a huge model and a low model, usually under the same hardness and skills. But there is a huge difference in cost, and with this I'm wrapping up. So if you want to run those models and do this analysis, you can see that Mimo, for example, costs 30x less than Opus will cost. So you can solve the same problem. They have the same capabilities by the end of the day. Both score the same, but you will pay $67 as median or up to $265 to complete a task with Opus 4.6, but you will pay $9 with Mimo. So like the economics are totally different. And that's great. That's good, because if you know it, then you can play in your favor. So conclusion, LLMs can help to automate basic parts of the causal analysis. They, in our eyes, they can reliably help to run a fully autonomous process yet. The LLMs, again, important, are just a single part of the agentic data science process. A good LLM with bad instructions and engine could be as identical to a bad LLM with good instructions and engine. So it's really important that we also understand that ecosystem matters. And finally, if LLMs are better at data science, that doesn't mean that they are better at to doing data science in the way that you need under your bounded or constrained space, space organization or conditions or requirements. And that's also what is not being presented in the benchmark. So hopefully we are releasing this coming soon. So if you stay tuned, hopefully in July we will have a name at least for the library, and we can put this so you can just test your skills for whatever problem you have. And I think that that's it. Thank you.
Thank you very much, Carlos. It is indeed a very exciting topic. I think that was the perfect way to finish this event. So first, one thing that is probably reassuring to a few hundred people that are still listening is that we still have a job. We cannot automate fully cutting edge causal inference with LLMs yet. One very quick question, because it's already late and it's definitely not your fault. So please connect on LinkedIn with Carlos if you have further question, and stay and keep an eye on this work when it will be live. So one thing, when you mentioned Opus 4.6 or 4.7, did you play with the effort level, or did it make a change?
Yeah, we actually made several setups. Right now, we were just showing like the default, which I think that is mid. So we definitely expect that once you play with the effort, he spend more time thinking. What we saw usually is that increments the cost, but it doesn't increment the rate too much. And to be honest, these are sadly not even in our setup. And one reason why we're doing Bayesian is so we can have a few trials. Someone asked about that. We want to have a few trials, and hopefully with the right priors have a strong verdict even in the absence of many iterations, because those iterations cost money. And to give you an example, because this will be public soon, we spent like $500 in a single evaluation for a single set of causal problems. So like if you want to test it yourself, then you will need to have the buckets with Opus to spend like thousands of dollars on different evaluations from different sizes and scales. And yeah, that's just probably a monetary constraint.
Yeah, definitely. I played with Fable 5 for the brief time I had it. I had access to it, and my first prompt led to burning 4.2 million tokens and costed $200 with a single prompt. But of course, it was a huge task and execution task of writing a 46 pages paper. And with ultra code efforts, Fable 5 decided to create and spawn 45 agents, sub-agents, I think, and this typically will make the cost explode.